Hello, this is Connor Davis, and today I'm going to show you how to create and package your own custom IP block in Vivado. So to do this, I'm going to use an example that uses the Base 3 board, which has an Arctic 7 on it. And for this example, I'm going to use a timer, a 32-bit timer. That's what we're going to create as a custom IP block. So we're starting off with this timer32.sv file, and I've also created a CPP file that will be for testing once we get to the Vitis stage of this. And now we're going to go ahead and start creating the project. So to start off, we're going to do, this will be an AXI peripheral, AXI, by the way. So we're going to continue on. We don't have any files to add yet. So the first important part is we're going to go to boards. Since we're using the Base board, we're going to search up Base. And we'll see Base here. If it doesn't automatically show, you'll have to hit refresh, and then it should show. I already have it downloaded, so I don't need to hit an install button. Instead, for me, it would be an uninstall button, which we don't want to do because we're using it. So we're going to continue on. We're going to hit finish, and we're creating the project. And now that we have it open, first thing we're going to do is go to Tools. We're going to do Create and Package New IP because that's what we're doing. And we're going to click Next. This is going to be an AXI peripheral, as I said earlier. And we're going to call this my timer because the CPP file that I've used, or that I've already made, depends on it being called my timer. We'd have to change some things otherwise, not a lot. It wouldn't take too long, but just for convenience sake, we're going to name it the same thing. We're going to go to Edit IP because we haven't made it yet, so we still need to change things. And this will open up a new Vivado instance and project. So yeah, what it's created right here is it's created a project that has two files in it already. One being this base mytimer v10 file, and the second one being this mytimer v10 S00 AXI file. So this S00 AXI file is what we'll be editing for the most part. But before we do any of that, let's go to Add IP, and actually, before we can even go to Add IP, we need to put this timer32.sv file inside this newly created IP repo, because that's where this custom IP block, that's where the project is run out of. It's run out of this IP repo directory. So we're going to add it to there, so we can add it to the project. And then we're going to go to Create New Design Sources, Add Files, and then timer32.sv. So we're adding that. And now we have that in there. And since I already have the file changes, I'm just going to Control A, Control C to copy. And then I'm going to Control A and Control V. And then I'll explain the changes I made. So first off, we've added some parameters right here. We've added a period and an enable bit parameter. So this enable bit parameter, this is for everything that I'm changing here, is mainly to make it work with this timer32 file that we've added. Let's see. Yep. And now it shows that this timer32 is going to be instantiated as T1, quote unquote, in this file. So we now have the top module is correct, and we have it keep going with the submodules. So this enable bit, we're setting to 1 because as soon as this starts up, we want the timer to start counting. The period I've set to an arbitrarily large number. You can't let it be too large though, otherwise it will be more than 32 bits. So I've just put it to this, which seems to work fine. And we're going to go all the way down here. This is where we actually instantiated the timer32 module. Here you can see the parameters that we passed in. And so here for the clock, we're just using the base S AXI A clock. That's what's being used as the clock for the AXI protocols. And then in this AXI protocols, they have 4 registers, as we defined earlier when we were setting things up. So this would be SOV reg 0 all the way to SOV reg 3. So for the input, we're taking things out of SOV reg 0, so just register 0. I'm just going to start saying register 0 and know that I'm talking about SOV register 0. And so yeah, so for register 0, that's what we're putting as the input for DN. And then for register 2, we're using different bits of that register 2 to be different inputs into the timer 32 module. The reset line is going to be the 4th bit of register 2. The write enable is going to be the 0th bit. The read enable is the 1st bit, and the 2nd and 3rd bits are the address input. And then the tricky part actually here is D out actually. So because it's an output, it has to be a wire. And so because of that, I've also added an additional, this line wasn't here before. I've added an additional variable. It's going to be a wire, and it's a 310 wire because it's 32-bit. Another way you could write this that would actually be technically more semantically correct with the design style of this file would to be put it as a CXI CS AXI data width -1, because this would be 32 minus 1, which is 31. So it's the same right now. However, if you were to change this CS AXI data width value here, then it wouldn't break things as easily because this would all be the same. But either way you do it, doesn't really matter. And yeah, so that's actually, I think, everything for this IP. So we should be good from here. And then now what we need to do is you need to run implementation. So this will run synthesis and implementation. And once we do this, this is to verify that it actually works properly. I'm probably going to skip some of this video to whenever this finishes because it's going to take a while. But after this, what we're going to have to do is we're going to go to edit packaged IP. And once we go to edit packaged IP, you'll see that some of these have green check marks and some of them don't. We want them to all have green check marks. The warning sign, this yellow warning sign, is actually okay. We can just ignore that. You can pretend it's a green check mark if you'd like. Because it's just a warning. Doesn't actually mean anything that we care about, at least. It does mean something, we just don't care. And so these ones that have papers, what an icon that looks like a paper and pencil, these will have actions that Vivado can automatically solve for you. So right here, it wants you to merge changes from file groups, because I'm guessing the file groups, like right here, it says 2 and 2, there should be 3, I think. Yeah, it should be 3 and 3. So it had to add more files to the file groups. And then for view and package, IP has been modified. So you just hit that, and then you're good. And then you should be able to hit repackage IP. But I'm going to wait till my thing finishes doing implementation. I don't actually think you have to do synthesis and implementation, but I do it anyways because it's a good sanity check. But yeah. Is this still recording? I can't tell. All right, so now it has finished running implementation. We don't actually need to open implement design, so we're not going to. And then here we're going to go to repackage IP. Now it's finished packaging my timer v1.0 successfully, and it tells me the file location. Do I want to close the project? Yes, because we are done with that. We don't actually have anything else we need to do there. So now we're back to the base project that we created earlier. So the first thing we're going to want to do, since we're creating a system on a chip design, we're going to go to create block design. We're just going to let it be block design 1 because we don't really care what it's called. It's not a big deal. All right. So now it's created design 1. It starts off empty. So we're going to go ahead and hit this plus sign, start adding stuff. First thing we're going to do is add a microblaze. And so we're adding the microblaze. And then we're going to hit run block automation so we can fill in some stuff for us. We want 128 kilobytes memory, so we're going to do that. Peripheral AXI port, we want enabled, new clocking wizard, debug only. And that should all be good. We don't need an interrupt controller. And so it's going to do some of this for us. So we're just going to wait for this to finish. All right. Now, first thing we want to start messing with is this clock wizard because it's not quite right. So right here, we want to make it use a system clock input. And then, yeah, so you see it has reset clock 1. So there's no longer a clock 2 input because we don't need that. The output clock, 50% duty cycle, 100 megahertz. That is good. That's what we wanted. Okay. Cool. Yep, that looks better. Now, what we want next is, so we already have this debug module. We have processor system reset. We have local memory. Let's go ahead and actually add our module. So this is what we just created. This is my timer V 1.0. If this doesn't already show up, you will have to go to IP catalog. Actually, you don't click IP catalog here. You would go to File, you go to IP, and forget if you go to a new location or open location. I think you go to open location. Yeah, you go to open location. And then you would select the location. So this be this IP repo folder that was created earlier. That might, if that doesn't work, then you do create new location. I forget which one. I haven't done it in a hot minute. Anyways, but yeah, so since I already saw it, we can just go ahead and add it. This custom timer module, which is what we just made earlier. So, yeah, and you see it says pre-production. That's something you can actually ignore, but it's another way to indicate that it's made by you. And so another thing we're going to need is we're going to need a concat. Actually, I don't think we need the concat, but I've been using it, so we're going to continue to use it. This is for reset lines, or interrupts. This is for interrupts, not reset lines. We're going to need, let me see, what all was it that I needed again? So we have the debug module, we have the microblaze, we have the local memory, we have the processor system reset, we have the concat, actually interrupt controller. We need an interrupt controller. Let's go ahead and add that. We'll go ahead and connect that manually. And then we'll connect this to that manually. Because sometimes those wire up wrong, even when you run connection automation. We're not going to run connection automation until we finish adding all the blocks on the board, just because we don't want to have to run it more than once. It doesn't take long or anything, it's just annoying. So we need a UART light. You could use the UART 16550, but that's more robust than we need, so we're just going to put the UART light on. And then after that, another thing we need is our GPIO, because we're going to use GPIO to connect back to our board so we can see some console output and see what the timer is actually doing. This GPIO we also do need to do some messing with. So we're going to connect this GPIO to 16-bit LEDs on the basis board. What we're going to do is, so the timer, its counter, since the timer is 32 bits, its counter can go up to 32 bits. But we only have 16 LEDs. So we're just going to show the first 16 bits of the timer onto the LEDs. If you wanted to, you could customize it and make it not 16 bits, but we're not going to do that. So, yeah. Anyways, further on, let's keep going. We have the UR light, we have the AXI GPIO, clocking wizard, we already messed with that. So we need the AXI interconnect. That's, yep, AXI interconnect. Another thing we need is, no, actually, that might be it. All right, let's go ahead and run connection automation. We'll see if something's wrong real fast. All right, now that looks awful. So what we're going to do is we're going to go down here and click regenerate layout so it looks a bit better. Yep, 5 things on this side and 5 things on this side. That should be right. Yeah, because we have the UART, connects USB UART, GPIO, which connects to LED. We have the timer, which does what we told it to do. We have local memory. We have the debug module, the interrupt controller. The concat's not connected to anything yet. That it needs to be fixed. I thought this looked a bit weird. Something's wrong with the interrupts. Here it is. I was like, there's an interrupt missing. Boom. There we go. And let's regenerate layout again, just for my own sanity. And now we have the concat right there. Yeah. So, yeah, the UART light is now connecting through interrupt to this concat. The concat then connects to the AXI interrupt controller, which then connects to that. And then we have debug module, system process reset, clocking wizard. We have 16 LED, 16 bits, AXI GPIO, AXI UR light, and the my timer. And yep, that's for peripherals. We're good. So this is the basic design that we're using for the system on a chip. So now that we have this done, we can go back to sources, and on this design, we can click create HDL wrapper. We're going to let Vivado manage the wrapper and auto update because we do not want to have to do that ourselves. And then now we're going to wait. In the meantime, we're going to take this constraints file, which actually defines the ports for the 16-bit LEDs that we're going to be using. We're going to put that in the main project. We're going to have to include it as a constraint source here in a second. All right, so this wrapper is finished doing its thing. We're going to add a constraint source, like I was just saying. So create a new constraint source, add file. It's the wrong place. Project 1, base2master.xtc. Cool. And we're going to finish. So now we've added a constraints file. And with this wrapper and the constraints file together, we can now, we're going to run implementation and we're going to run bitstream. So we'll also run synthesis. And yeah, so we need the bitstream, which is why we're running synthesis and implementation. If there's any problems with your synthesis or implementation, then you've messed up somewhere. But yeah, since this is going to take a while, I'm going to skip ahead to once this finishes. Okay, so now the implementation has completed running for me. So we're going to go over here and we're going to click generate bitstream because that's what we really want here. And yeah, so now it's going to start running the bit stream, or generating the bit stream. This might take a while, so I'm going to skip ahead. All right, so now I've finished generating the bit stream. So we are actually going to do open implemented design. I'm not 100% sure if this part's necessary, but we're going to do it anyways. And once we open the implemented design, then we're going to go over to File up in the top. Let's let it finish opening. Okay, now it's opened. So now we're going to go to File. We're going to go to Export and Export Hardware. So we're going to click Next. We're going to do Include Bitstream. This will include the bitstream that we just generated. That's why we needed it. We're going to go Next. This will generate a .xsa file. We're going to call this Design 1 Wrapper because what it's called doesn't honestly matter that much as long as we remember what it's called. And yeah, so that's finished being generated. Now we're going to open up Vitis or Vitis or Vitis. I have no clue how to pronounce that. Anyways, so we're going to go up here to File. We're going to go to New Component, and we're going to go to Platform. So we're going to just let it be called Platform because it doesn't really matter. Hardware Design, and we're going to do Browse. So what we just made earlier was this .xsa file, and that is what we're going to click on here. We'll select that. We're going to go Next. It will automatically now create a operating system and processor choice for us with the specifications for the board, the FPGA setup, and the timer block that we made. Yep, okay, here we go. Yeah, for the microblaze, which we did use the microblaze processor. And we're going to finish. So now here in a second, it should show up. Waiting for that to finish though. I'm going to do that. Actually, this doesn't matter. Yeah, so you can see down here, it's still running. It shouldn't take too long, so I don't think I should need to skip ahead, but yeah, I'll just I'll skip ahead to when this finishes. Okay, so wrong window. Here we go. So it has finished running. So it just generated this platform. What we're gonna do is we're gonna go ahead and build it. You can do this now, or you can do this later. It doesn't really change much. So anyway, but it does need to be run before we run the next thing we make. After this, we're going to make a application. So we're going to go to New Component. But the application we're going to make will be from examples. So we're going to click on Hello World, and then we're going to do Create Application from Component. Create Application Component from Template. We'll just let it be called Hello World because we don't really care. We're going to do Next. So this is the platform that we just made. See, it has the base 3 board. It's embedded with the vendor of Xilinx, which is what we use. So then we're going to go Next. Standalone microbase. Yep. Next. Next. Finish. Okay. So that should, yeah, you can see creating a Hello World component. That should pop up here in just a second. Yep. That was much faster than the other one. All right. Now that we have this going, this Hello World, where sources. I was looking at the wrong place. So we're going to open up this hello world.c, and as you can see, it's just this basic file. Well, if you're following along, then you probably also have the files that I have provided. So I've already made this. I think I already talked about this, but I've already made this .cbp file that I called hello world testing file, but what it's called doesn't really matter because we're going to do Control A, Control C to copy it. and we're going to go back to this Vitis window. We're going to do Control A and Control V to paste this. So this is a test bed for the custom timer block that I made. So just a little short description of what this does. So we've done a bit more includes here. We've included a sleep so that we can actually see the changes in the LEDs, because there's times we're going to output to the console. We're using a putty console, by the way. Because we're using a USB connection to the base 3 board. So there's times where we will output something. We're reading the output from the timer module, which will be the current counter for the timer. And that value will also be put on the LEDs. And so for the point of us actually testing and seeing to make sure the values line up, I've put in time sleeps so you can check them. Anyways, this X parameters file that I can go to, if you control click on it, you can go to it. You don't really need to, though. It's just me to show you. So here's the definitions for the addresses for the custom IP timer block. So you have the base address and the high address. Anyways, we can go back to the normal file. And you also have this include, actually, I think this was already there. But yeah, so, that's not, we're gonna do a world. I don't know when that got changed. I don't know why I went back over to the, I don't know why I went back to Notepad++, but anyways. So first off, what we're doing here, just a little description. So this XGPIO set data direction, this is setting up the LEDs. This will set up the LEDs. This 1 shows you as channel 1, and 0 shows it as outputs. So this is actually a mask right here. It's a bit mask. Anything that has 0 for this bit mask will be set as an output, and anything that was a 1 would be set to an input. So this is actually a much longer string, or not string, but number, as in like how many digits it has. But they're all 0, so we're just putting 0 because simplification. Anyways, so we have a discrete write right here, which this is taking from this base address. We defined this up here. Actually, I probably should have explained it. So up here, this is the base address that I was showing you earlier from the parameters file. So this is for my timer. This is the address of the registers. So if you go back over here, this right here, this base address +1, this is getting the value from register 1. Down here I have base address +0. That's the value at register 0. And yeah, down here we have base address +2. That's value at register 2. So what I'm doing here is right here, I'm writing the values in register 1, which is the output. If you remember back from how we configured this earlier, register 1 has the output. We're putting the output from register 1 into the LEDs. So we're setting the LEDs to the value in register 1, which is the counter. The counter on the timer. And then we're doing that a good bit. Most of what this is down here is we're changing the values of read enable, the address, and reset. You can look at it yourself later if you wish. I'm not going to go too much more into detail in here because the video is getting long. But anyways, on to testing this. So this should now be good to run. So we're going to go ahead and build it. No pod point found. What? Oh, I know what happened here. Okay. ignore that. All right. So I restarted Vitis because I had it open for multiple hours now, and had created and deleted multiple platforms with the same name. So I decided to restart it because it was very likely that was causing the problem, and I was right. That was causing the problem. So anyways, you can already see the green check marks. You already know it ran just fine, but I'm going to run it again anyways, just to show it running perfectly fine. Yep, and you see a build successful right here, and this also says this is build finished successfully. So we're good on that. So Hello World has now built, and I already copied and pasted the new code in. You'll see there's a lot of things like this right here, but this is all because it doesn't recognize this right here, even though it's it actually does find it. It's just the IDE doesn't think it can. Anyways, that can be ignored, is what I'm saying. So we're going to go ahead and I'm going to turn on my board now. And we're going to open up the putty session. So since I just turned my board on, let's reset the terminal, clear scrollbacks. I don't know if I had any, and restart the session. So if you're just opening up putty, what you're going to want to do is you're going to want to do a serial port. You're going to have to go to your device manager, figure out what COM port you plugged into, and then do a speed of 9,600 because that's the baud rate. And then, yeah. So you'll do that, and then you click open. But I've already done that, so I already have this on. And I already have my connection. Now I'm going to click run right here, and we're going to watch the output to the console as this runs. And you can't see it, but as this happens, LEDs will also flash on my on the board. As you see, I have an outputting device for the LEDs as well. And yeah, that is the entirety of the base test code. So yeah, it's working. Another thing, just to, I guess, show it working a bit more, that you can do is I have this right here. If you uncomment that, I just press Control and then backslash because that uncomments things. It's a shortcut. If you do that and then you rebuild, this part isn't necessary. This is just an additional thing you can check or just something cool to see. And then you click Run again. We'll get some more cool inputs. This is Hello World. That's the marking of the new program. And then yeah, you'll see the timers incrementing up. And then I don't know if you can catch it, but once it hits around 005, or no, just 05 F is where the period marker is. So this will only loop up to 05F and then it will restart. AXI protocols take more than one clock cycle. So this 32-bit timer, because it's using AXI protocols, we can't actually track every timer tick up. Not with the console, at least. The timer itself does track every clock cycle. But yeah, so that's that's how to make a custom IP block in Vivado, and also using Vitis as well, I suppose. Yeah, thank you.